Day. In the last set of lectures, I said that the poker game is the method that is the most used in the in time estimation. However, I said that a big company now they are not satisfied with the inaccuracy of these of the existing methods, and they try to use the advances on machine learning to have better time estimation. So, company like SAP or other big company, they want when they promise that they are going to deliver a specific project, even if it's internal, in 6 months, then they are going to deliver that. And if they ask for a specific budget, then they want to be close to the truth. So, with the approach of estimation using the poker game, the common expectation is that we're going to have an error margin of 30%. But big company now, they do not tolerate those 30%, and they want to have they'll tolerate a margin of error to the best about 10%. So how are we going to get that time estimation? What would they do? This is part of if they are using, I said big company before, that they use capability maturity model. And even if they do not have the formal certification, in general, big company, they have that. So we have here a context, and I want to get an accurate budget to fix bugs. And here, in general, those are the activities that we need. And the question is how to get an accurate time estimation to fix bugs. We want to have better estimation. Here we are talking about security bugs, but that as to any other activity, things are the same. Um, and is how to estimate the time to fix security bugs. So if you Google estimate project time, and I'm sure that many of you try to do that, you're gonna see here step one: understand the project outcomes, estimate the time, then complete the project. Then you can begin to estimate how long each will take. So similar to what we've seen in class, this is the common practice, right? So, and example of model, mathematical model here is the COCOMO model, which is old 30 years ago, 30-year old. And this model was developed based on a database from NSA, from the NASA. The NASA, they have a project, set of project, and they have the time that they spend on each of these projects. Then the researcher, they try to develop a model, and they make here an exponential model, not this model, in a way that they could have an expectation of the time that should be needed to develop a new project. And we have here the expected time for a project is a coefficient A multiplied by the number of thousands of line of code, exponent coefficient B. And they have here three types of software. This is organic, this is the semi-detached or embedded. And let's say the coefficient A for the organic was 2.4, the coefficient B is 1.05, for semi-detached is another coefficient, and for the embedded, the coefficient are again here different. So they categorized the set of project based on the category of the project. Then they inferred based on this using regression model here, what is the coefficient A and the coefficient B and B, the exponent B for that. The main limitation of COCOMO model is 50 years ago, we write code software and we might write only few hundred line of code. And that might be assembly or low-level software. Still, 30 years ago, we can expect 1 million line of code, but a developer now can write probably this 1 million line of code by himself in specific duration. So estimating the duration of project based on expected line of code, thousands of line of code for the project is not possible anymore since the project they become very big and you cannot You cannot talk about, I have a project, let's say, website that I'm going to develop, and then I am going to write, let's say, a 1,000 line of code. It's possible that I change the framework, then because I changed the framework, I'm going to write less code. So from this few thousand line to, let's say, 200. And does it mean that I'm going to spend much time based on that coefficient for to develop the software? No, because it's possible that I will gonna also spend time for the configuration and so on of that software. So the Kokomo model, it has several limitations, including the unknown size of expected software and so on. The method that we talked about for the estimation method talked about before are the expert judgment, the Analogous estimating, the parametric estimation, the 3-point estimation, group decision making estimation. We said that the group decision estimation is the best, but basically here also we have a margin of error that we get there. And also it's a rolling wave method where you could do the estimation. Your accuracy in the estimation are good in the short term, but in the long term, they are not that good. So you might multiply your estimation by 2 for the long-term activity. One of the methods that I talked about is the parametric estimation. And in this parametric estimation, I said that you could have a set of factors, then you could apply machine learning. We applied this method in the estimation of security bug fixes in SIP a few years ago, I think 4 years ago, 5 years ago. And I'm going to post a link for the paper that we wrote about that. And I'm going to talk here in this lecture about that method. So in a research, we ask the specific scientific question, but in general, we need to refine the question to smaller set of questions that we can verify. And the verification of this research question, we can develop algorithms and then implement this algorithm and assess their capability set of features for this algorithm. We might do empirical study, and empirical study here, it could be that we communicate, we talk to practitioner, or we assess existing software or existing documentation, and we get some themes from this information. We could also use simulation where we write, let's say, the rules for the approach or for that govern the idea that we have, and then we give it some data input similar to the one that are in real life. And here I use similar. So we mimic the real life using the simulation. We mimic the data using also the simulation data. And then we extract the evidence and we check the evidence that we got, whether this is themes for empirical study, whether these some statistics for algorithm implementation or simulation, also statistics. And we think about the relationship between this evidence and our earlier question. How good did the approach show the answer? The evidence was good to confirm or deny the question that we have. So let's say here for the case of SIP, they use here a set of programming languages and a set of tools to identify security vulnerability. So the language that they have ABAP, they write also code with C, C++, they write code with JavaScript, with Ruby and others, including Java here. They also use a CVA, Silent here for security, which is their own tools for ABAP. They use Coverity for C++, checkmarks for JavaScript and Java, and also they use Fortify here mostly for Java. The vendor for CVA is SAP, the vendor for Coverity is Synopsys, and the vendor for checkmarks is HP. So they need to apply those testing for multiple billions of lines of code, not millions, but billions of lines of code. And they have a lot of configurations they use for their software, and they need to check all the products. They would not deliver a product to the customer unless they checked for all the security vulnerability that are of high priority for them. So our research question, is there a more accurate estimation method? And the goal here is to identify, the first goal is to identify the factor that impact the fixing time. what factor might impact that. And to get that, we interviewed participants in the vulnerability fixing process. We talked to developers, to security experts, and so on to get what are the factors, in their opinion, that impact the time that is needed to fix security vulnerability. And the result was the major factor that impact the fixing vulnerability. We have here a summary of this list. So we say, for example, the vulnerability characteristics. So there are 6 factors in this category, and 9 of the developers, they report out of 11, they reported this. The software structure, so complexity of the software, the parameters that are in the software, the number of parameters and so on, we identified 19 factors, and 10 of the interviewed participant reported items related to software security. See here that the experience and knowledge, we found 12 items related to factor related to experience and knowledge, and this factor was reported by the 11 interviewed people. So they reported that experience and knowledge are have a big impact the time to fix security vulnerability. So now we have the factor that impact the security vulnerability. We ask now, the challenge is, can we predict the cost of fixing a given security vulnerability, new security vulnerability that we might have? And to do that, we need to model that the vulnerability fixed time is a function of a set of factors, x1 to xi. So we have here identified a set of factors, but basically in this second time, we need to identify the f. But obviously, we do not have all the access. We did not have enough data for all the axes. We have data for only a set of axes. So we're going to have the f not for the all axes, but it's going to be f of a set of data, set of factor that we know. And we assume that the others are not a variant, which is obviously no, but they would not have much impact. This is the assumption. The other factors do not have much impact. So we got a set of data sets here, and some they were a few thousand. I think most of them they were millions of record. So SIP has a set of static data analysis data for ABAP code, which is dataset 1, static analysis data in Java and C code for dataset 2, and security message, those are for vulnerability that are reported after they released these software. So some companies or some developers, they reported these vulnerability. They have also data sets that describe the different component for different software, and some data related to the projects. So the research method was to specify the set of questions. We collected the data set that they provided. We prepared the data so we could use them. So we added the nulls and whatever cleaning of the data that we would need. Then we explored the data. I'm going to show here how to explore data to understand basically here the data. Then we develop a set of model. We analyze the model with the expert. Then basically there will be some knowledge that we gain from this analysis. We introduce this knowledge into the models. Then we develop again the models and we analyze them again. And at some point we found that we need other set of data, because we need other set of data. Then we collect more data, go prepare it, clean it, explore, and so on until the so an analysis, if we got satisfactory performance, then we would use that. So in the data exploration here, I see that I show that here a graph, and we see here that we have denial of service or memory leakage or SQL injection, cross-site scripting. Those are the vulnerability type, and we see on the y-axis that this is the different duration that are spent, let's say, in the set of denial of service vulnerability, or to fix the reported memory leakage vulnerability, SQL injection. So with some, let's say it took a few days. In other, it took a long time. There's one here, vulnerability, as you see, it took over almost 1,305 years to fix the vulnerability. So that vulnerability was very difficult to finish it. So they have work around, but to fix that, they needed much more time to work on. So in this project, we used three regression method: the linear regression, the tree-based regression, and the neural networks. If you want more details about these, I have a book chapter on that, so you might see the book chapter. You can Google myself or see my scholarship website on Google, and you will find an introduction to machine learning where I describe these methods and other methods. So in order to evaluate the performance of each model, we would use a set of metrics. And here, the first metric that we use is the coefficient of determination, which is used basically here for the linear regression. But we also use the prediction level. And in the prediction level here, we give an error of 25% for each prediction value. And we check whether the predicted value is within the 25 margin error of the actual value for the tests. We used also the information criterion, which is here the rate of information losses, a metric that is used mostly in the tree-based learning. So we can see here, this is a tree-based portion of the tree-based learning, and we can see here 247. This is for, I think this one is for the linear model, and we have an intercept. Then the code scan tool, they have their coefficient, the central security coefficient, the customers. We can see even for the customer, they have impact on the time that is spent on the security vulnerability, right? So the test services, the validation services, and in the right here, we see that we have here vulnerability type. There is others there, and those are the different codes. So there is memory leaks, XSS, cross-site scripting number 2. And here, those are some metrics for the tree. We have here a set of components because they have thousands of components. So those are the code of component for the first one, and there are metrics at the end here for that. And we have 168, that was 168. The second category of components, here we have another second category of components. And also because of that category, if the project is within those, is one of these categories, then the estimation follows another branch of the tree. So we estimated here, we computed the performance metrics, the residual, the AIC, and the PRED, the metrics that I discussed before, for the different, based on the three data sets. The first one is the ABAP, the second one is C++ and Java, using Coverity and Fortran. They combine these data together. And the third one is security message, which are related to software that were released, vulnerability. And we can see here for the residual that, for example, the ABAP is 0526, but the security message is 0944. The IIC, this is here, the number also is different. So the loss of information, as long as it's a small, that implies that the method performed better. So when it's a smaller, then the performance is better for IIC. And the PRED here, this is the proportion of the tests that the margin of errors is within 25. So we can see for the linear regression, the best method for the ABAP was the linear regression. We have 31% was within that margin. And the 68% here, they were outside of the 25% error margin. For the C++ and Java, the neural network performed the best and gave 33% within those 25% error margin. And in security message, the error part here performed the better. So we can see that the different machine learning method performed differently in the different data sets. However, we see also that from business perspective, the management tell us that if this 25% I could agree with, because this is now we compare to agile errors range, and but this only you have only 30% prediction within these 25%, and 68 are outside of this margin, so we cannot use these models. So we come up, what do we need? We need one of the strategies to look for other data sets or other factor that might impact the data. And we come up, we did not have more data, but for software, Java and C++, we can extend, we have other data sets that we could use. And here we can see when we use the extended data sets for C++, that for the linear regression here, we have one for AirPod, so it's reduced to 463, and for LR100, so we have an overfit in this case. But for the extended security message, we got more information related to this data, to this security message. Then the regression is 0909. The error part is for 6421. There is no much improvement from 6507. But the neural network performed very well on the extended dataset for security message. This is provided 65% 05. So when we talk about 65 here, they would say, well, actually, if you approach 80%, then we would use this. But if it's less, then we cannot give it to the user or to the developers, and we can tell them that to fix the variability that you have, you're going to spend, let's say, half a day or one day, and your prediction is already within that 25% error margin is less than 80% accuracy. So 1 out of 5 is already more than 1 out of 5 is wrong. And here, you have a true two that you're going to be within that margin, and one is outside. So still, it's not satisfactory. So those are here the above 31%. The extended C++ is 100%, but this is over fit. And the last one is the security. So we said that this is not satisfactory. What is wrong? And we took the data, for example, for the security message, and this is the security message, they collected data from 2005, since they started fixing the vulnerability, until 2015. And we want to check what is the average time, the average duration for fixing a given vulnerability. And we can see that at some point, this average time, it goes up. So at the beginning, they did not spend time. Then fast, they spend a lot of time until they reach, let's say here, 400. Then they fixed a lot of vulnerability, assume that they have ways there to fix some category of vulnerabilities, so they find the solution how to do it. Then again, there are new vulnerability potentially that they were discovered, and they needed a lot of time to fix these. So this set of vulnerability, they needed a lot of time. So we can see, however, there is a tendency of increase in the time, in the mean average time. So this applies for security message. Again, for security message are the vulnerability that are already in published software, but the vulnerability that are discovered using for Coverity and so on. So we can see that there is another similar dependency, although the curve here is different. So we can see there is a difference. And basically, this is this increase and decrease. So we provided this information. Now we can see that there is a tendency of increase. So that justifies that those predictions accuracy, they are not good, because it looks like the time is an important factor in these models. So the time increases, time spent in fixing vulnerability increases. But when we gave already these curves and to the business, they say, yes, that is true that here we increase and then this decreases, because we do at the end of the sprint review, we fix these vulnerabilities. So we check them, we keep the ones that are more difficult, but before releasing a specific, let's say, sprint or specific release, we address these vulnerability. We give them to expert, and the expert, they fix these, and then the duration is fine. So we can see that several factors beyond, several aspects beyond the defined metadata impact the time that we would spend to fix security vulnerability. So out of this, we developed a prototype. So we developed a data analysis engine that implements the prototypes that developed before. And this data analysis engine communicates with the dataset themselves. So that they have, or this is a clone of the data set. And we have in that data engine, there is a prediction function, there is importance of factors and prediction accuracy. And we try to work on a web application that it's easy that you can access this web application and you can provide a set of information for the vulnerability, and gives you it gives you the time that you expect. When would you expect to finish the time? Here we have the duration of fixing, where it's possible that the developers, they do not work on the specific vulnerability, but the time it takes to fix it, to release the fix for that particular vulnerability. This is what we cared about. So the question was, is there a more accurate estimation method? And the method here that we applied machine learning techniques using a set of data sets, with the evidence where the performance of these machine learning techniques is that good enough. The information was not good enough, because still we actually did not continue here in this work because the budget was over. And otherwise, and there was no much promise at that moment. There is no budget to continue the work, and the promise also we needed to collect more data and to come back to that, but we did not come back to that. So this is example on how we use research into addressing a question like, for example, here, having accurate estimation of the time to fix security vulnerability. I will post